In our universe, every galaxy is racing away from all the others, each one inexorably flung into the deepest regions of creation, traveling on an uncontrollable journey through space-time that will not end until the embers of all their stars have faded into darkness. It is generally thought that the gravitational attraction of all the matter in the universe, both seen and in the form of dark matter, is not enough to overcome the forces of acceleration driving the expansion of the cosmos. This means that the future of creation is intricately connected to the second law of thermodynamics. The decay of the universe has begun. If we accept the implications of the current observations of universal expansion, then the future of the universe is rather bleak. The inexorable tide of inflation will ultimately land the cosmos on the shores of desolation and heat death. About 155 million years after the Big Bang, the first star formed. And ever since, stars have forged from coalescing gas, where the pressure of gravity ignited the star's fusion engine. This epoch in the lifetime of our universe is dominated by the processes that cause the stars to shine. Most of the radiation during this time is due to the stellar fusion of lighter elements into heavier ones. This is the age of the stars. We currently reside during this period in our universe's history, and it is known as the Stelliferous Era. Of all the stars in the universe, only 20% of them are the size of our sun and larger. This includes blue giants, red giants, and all the main sequence stars like the sun. The remaining 80% belong to very low-mass stars. Most of the stars in our universe are red dwarfs. The lifetime of a red dwarf star is staggering. Because they have such low mass, they can burn their hydrogen fuel into helium more efficiently. These stars shine for over 10 trillion years. Since the higher mass stars live nowhere near this long, they will disappear first. Some as supernovae, and others, like our sun, as planetary nebula. Long after they are gone, all that remains will be red dwarfs, white dwarfs, brown dwarfs, neutron stars, and black holes. Also during the Stelliferous Era, almost 100 trillion years from now, all galaxies in our local group will have redshifted so far that even gamma rays will have wavelengths longer than the observable universe. The galaxies will have disappeared. As the red dwarfs slowly burn their nuclear fuel over untold millennia, over cosmic timescales so vast as to be meaningless to our brains, our galaxy, the Milky Way, will die. Stars will be flung out from random gravitational encounters, and the central black hole will also devour them until the galaxy itself no longer exists. The Milky Way is dead. Eventually, in 100 trillion years, the last stars will have died. All that remains are their corpses, white dwarfs, neutron stars, and black holes. Once the last of the red dwarfs exhaust their fuel, all nuclear fusion in the universe will have ceased. The red dwarfs have cooled into white dwarfs, and they, along with neutron stars and black holes, will be the only objects with mass still shining in the heavens. We have arrived in the degenerate era. Once the last star burns out, the universe will be a very dark place. But the feeble embers of the remaining white dwarfs will still produce some light. At this point in the life of the universe, they are the brightest objects anywhere. After the embers of the white dwarfs, brown dwarfs, and neutron stars have faded, some 10 to the 40 years hence, and all protons and neutrons have decayed into positrons and neutrinos, black holes will dominate the universe. Here, the primary source of radiation throughout the universe becomes Hawking radiation. Black holes cannot live forever. They are slowly evaporating. Small fluctuations in space-time cause particle-antiparticle pairs to appear close to the event horizon of a black hole. Due to the strong gravity so close to the black hole, one of the pair is captured while the other escapes into space. This feeble signal will be the only source of warmth throughout the cosmos. The universe is colder and darker than it has ever been. The average temperature is only 5 Kelvin. The lifetime of a typical supermassive black hole of 100 billion solar masses is about 10 to the 99 years. At this point in the lifetime of the universe, all that remains is diffuse matter. All activity in the cosmos has all but stopped and is in an extremely low energy state. What happens here during this so-called dark era is unclear. The universe may stay in this state forever, this heat death signaling all that remains of a once active and vibrant universe.